Hello everyone. Our tool is SocNetV. Myself Ishita Saxena and my group members are Nukala Shreya, Animesh Singh, Aditya Sharma. SocNetV, as the name suggests, social network visualizer. It is a cross-platform, user-friendly, free software application for social network analysis and visualization. It is developed in C++ and Qt. It runs on Linux, macOS, and Windows. With an intuitive graphical interface, users can effortlessly draw networks, import data from various formats, example GraphML, GML, PageX, and modify them as needed. With SocNetV, we can draw social networks with a few clicks on virtual canvas, load field data from file in supported format, crawl the internet to create a social network of connected web pages. It will be discussed later. We can edit actors, which are nodes, and ties, which are edges, through point and click, analyze graph and social network properties, produce beautiful HTML reports, and embed visualization layouts to the network. Now I'll be discussing the user interface overview of SocNetV. SocNetV has a simple graphical user interface GUI composed of the menu, which is the top portion of the full screen, which you can see over here, the toolbar, which is right below it, the panels, which are on both sides of the canvas, and the canvas, which is the white working space. In the figure, this is an example of a SocNetV main window. All of these will be discussed in detail. The menu. It consists of the network. Network has basic options like opening a network, exporting it, printing it, and so on. The edit. It is used to edit the network, like create changes over it, modify it, and so on. Analyze. We can gain more information and insight about the network through the analyze options. Layout is used to change the layouts of the network, how we can see it, how it will be visually represented. Options and help. The toolbar. The toolbar is used to create, load, save, and print a network. It also has options to edit the nodes like add, remove, find, or find the nodes, change its properties. The edges, which can be edited by adding it, removing it, or filtering it. And we can open the application settings. The control panel. The control panel is composed of three groups of actions commands: the network, analyze, and layout. We saw them in the menu also, but they are further in the control panel because some of the important options of these three are listed out in the control panel for easy and quick access. In the network group, there are four submenus: auto create, which automatically creates random networks. There are various options available to create random network as per our choice. Subgraph, we can select a certain group of nodes and then create a subgraph out of it, like star, click, and so on. Edge mode, we can switch the mode to either directed or undirected edges. Transform, we can do various type of transformations on the graph, like symmetrize the edges and so on. The analyze group, as we can see in the image here, this is the control panel and all the options are listed in each category. So in the analyze group, we have matrix, cohesion, prominence, communities, and equivalence. All this will be discussed in detail later. Next, below is the layout group. It is used to change how the network will be visually appearing on the screen. You will find options to embed visualization layout to the current network. Now, working with SocNetV. Now we will see how we can tweak with the nodes and as well as with the edges to create different types of networks. Firstly, nodes. We can create nodes out of various options like double clicking on the canvas. For this, we will have to enable the mouse option which is present on the toolbar. If we enable this, then double clicking on the canvas, we can create a node. We can click on the add node option in the toolbar, or there is a keyboard shortcut of Ctrl+ to add a new node. Moving nodes. Again, enabling the mouse option will help us to move the nodes on anywhere in the canvas by just a left click and dragging it in the canvas wherever needed. Adjacent edges to the node that are highlighted when we click it or we drag it. Below we can see the node properties, like we will choose the node and like any of the number of the nodes that are appearing, and if we click on OK, then that particular node will be selected and we can change the property of that particular node as in a dialog box which will be showing later. Node context menu. If we right click on a node, it will open a context menu. The context menu has options like delete node, add edge, change node properties, and so on. Node properties. If we right click on a node and select the node properties from the context menu, the options it will appear options like color, size, label, and shape of the nodes. We can do all type of tweaking through the node properties dialog box. Node label display. By default, nodes are tagged with their node number. Enable the options in the menu, options, node, display labels to display the labels. This is the dialog box that appear when we click on the node properties after right clicking on the node. It has various options like node label, size, value, color, shape, and custom icon. We can change any of this and click OK, and the following changes will be applied on that particular node. Next, we move on to edges. Edge creation methods. Middle click or double click on a source node, then repeat it on a target node. This will create an edge from the source to the target. Right click on a node and select create edge. Then it will ask us to enter the target node and the edge weight. Selecting both of these will create an edge accordingly. We can click on the Add Edge button in the left control panel, then enter the source and target node numbers and the edge weight accordingly. Also, we can use a keyboard shortcut Ctrl+/ to create new edges and then provide the source and target node and their weights. Default edge properties. All edges by default have a unit weight, that is 1, and black color, and either of this can be changed with the edge properties. Editing edge weight. Right clicking on an edge and then selecting change weight from the context menu will modify its weight. As we can see below, if I right click on a edge, here I right click on a directed edge that was pointing from 2 to 3. So here it has displayed options like remove edge, change edge weight, change edge label, change edge color. Clicking on any of these will change the edge properties accordingly. Directed versus undirected edges. Middle clicking from a source node to a target node creates a directed edge. Repeat the process from the target node to the source node, it will create an undirected edge. The edge context menu. If we right click on an edge to access options like delete, change weight, change color, etc., it will change the properties accordingly. Relations. Relations in SocNetV is a useful option as well as functionality. Here here it tells what is the relation between the nodes that are present on the canvas. So if the relation between the nodes at present is friendship, then we can add a new relation like co-workers, and then the edges added between them will represent who works with whom. So the application prompts you to enter a name or label for the new relation between actors or nodes. A relation represents a collection of ties of a specific kind between the network actors. SocNetV supports multi-relational network. You can add more relation to your network by clicking the plus button in the toolbar. Next, we will move on to basic functions in network menu by my friend Shreya.
I am Shreya and I am going to tell you about some basic functions in network menu. Starting with loading a network. Users can load a network data saved in .gml format in SocNetV. SocNetV also supports some formats like GML, GraphML, PageX, etc. This can be done by going to network and then there is an option called import. selecting that, you get a file previewer window. That file preview window is to assist in selecting the appropriate code page for files created in different operating systems. SocNetV initially presents the file, and then on selecting it, you will be redirected to that graph. Coming to saving the network. Saving the active network can be done by just pressing the Control plus C on the keyboard, or by going to Network and selecting the Save or Save As option. By default, networks are saved in GraphML format, but users have the option to export in other formats like PNG or something else. Then coming to using a known dataset. SocNetV enables users to recreate some known datasets. This can be done by directly pressing a shortcut key called F7, or going to Network and pressing Use a known dataset. SocNetV shows the given datasets. You can select one of them and pressing OK. Then you can work on that dataset. Some of the known datasets here are Florentine families, karate club, and etc. So just by selecting the dataset, you can work on it. Then random network creation. SocNetV also enables users to create a random network. Some of the random networks are scale-free, small world, Erdos Renye, lattice, deregular, or ring lattice. Just by pressing on this, you can give the number of nodes or number of edges, and you will get a graph. You will get a random network. Then the fifth option is printing and exporting a graph. You can print the active network or the current snapshot of the SocNetV just by pressing Ctrl P. This will direct to your printer. Or you can export the current network by going to Network, Export, and you can select the format as well. Next, coming to web crawler. Web crawler, you can go to Network, select web crawler, or there is a keyboard shortcut called Shift plus C. So, SocNetV includes a web crawler feature for mapping hypertext links between the web pages. Users can initiate the web crawler to analyze relationship between web pages starting from a given web page or a website. Web crawler basically consists of a spider and a parser. Spider visits an initial URL, downloads its HTML, while the parser scans the href links in that particular web page, expanding the network. User should specify the initial input URL. Here, as you can see in the drop-down menu, there is a field called initial URL where we need to input the starting web page and set some limitations for each web page, like maximum URL links, or crawl only external links, show internal links, etc. Then upon this, the crawler traverses the web pages using the spider. It downloads the HTML code, and using the parser, it expands the network by visiting the href links. So this results in a network where the nodes are the web pages and the links are the directions between the web pages, or the relationships between the web pages. SocNet also provides some analysis methods. Now I'll be discussing the matrix analysis methods. SocNet provides the first analysis method is the adjacency matrix. Just by pressing the keyboard shortcut F6, you will get a HTML format of the adjacency matrix. Adjacency matrix is basically if a matrix, a square matrix, having n cross n, where n is the number of nodes. If there is an edge between I to j, it represents 1, else it represents a 0. So you can see a HTML format of the adjacency matrix for a particular graph. SocNet also provides an option for getting an inverse matrix of the adjacency matrix. Again, just go to Analysis, press Inverse Adjacency, and you get it. Or go to Network, Matrix Analysis, and Inverse Adjacency, then you get the HTML format of your inverse matrix. Then plot adjacency. SocNet provides an option where you can get a plot adjacency of the plot matrix of the adjacency matrix. This can also be done by pressing a shortcut called Shift F6 or going to Network Analysis, Matrix Analysis, and going to Plot Adjacency. This again provides your HTML in your web browser where you can see a plot matrix. Plot matrix is basically if there is an edge between I and j, it colors the matrix, it colors that block, else it is white. Then there is an option in SocNetV to find the transpose adjacency. Same, go to network analysis and transpose adjacency. You get the transpose of the adjacency matrix of the graph. Then you have the co-citation matrix. The co-citation matrix C is derived from the adjacency matrix A of the network. For example, A represents the matrix where each element Cij denotes the presence or absence of a citation from document I to J. The co-citation matrix computes C is equals to A transpose into A, where A is the adjacency matrix. Each Cij represents the actors linked to both I and J. Here, actors means nodes. And the diagonal elements in the co-citation matrix represent the in degree of I. Basically, Cij, that is the element of co-citation matrix, represents the number of times a particular node is co-cited or co-referenced in the network. Then we have the degree matrix. Degree matrix computes the degree of each node of a adjacency matrix or a graph. In the degree matrix, you have n nodes, n cross n matrix, where the diagonal elements give the degree of the node I. And then you have the Laplacian matrix, which is basically L, which is represented by L, which is D minus A. Here, D is the degree matrix and A is the adjacency matrix. It is an n cross n matrix. It captures the local connectivity structure of the graph. The diagonal entries represent the local structure of individual nodes, while the off-diagonal entries capture the pairwise interactions between the nodes. So these are the analysis methods that SocNetV provides for matrices. Next, we have the cohesion measures that also comes under the analysis methods, which is explained by my friend Anish.
Hello everyone, I'll be continuing the presentation with cohesion measures. So cohesion measures in networks actually quantify the extent to which nodes are interconnected or clustered together. They help assess how tightly knit the network is. As you can see in the picture below, comes under the analyze section, and I'll be covering all the cohesion measures one by one. So first one is the symmetry test. It just says whether the given network is symmetric or not. Naturally, all undirected networks are symmetric. Actually, symmetric refers to whether the adjacency matrix of the network is symmetric or not. So naturally, all undirected networks are symmetric, while it depends on whether the directed network may or may not be symmetric. Also, I've also attached the screenshot over here. This is actually a network which has been taken from a known data set. So earlier my friend actually showed how to load networks from known data sets. So I've actually taken such a network and calculated all the cohesion measures on that network itself. So this particular network was not symmetric, so it returned the adjacency matrix is not symmetric. Next is the geodesic distance between two nodes. Geodesic just basically means the shortest distance between two nodes. So it asks us to enter the source node, the target node, and just returns the geodesic distance between them. Next, cohesion measures the average distance. It just takes geodesic distance for all pairs of nodes and takes the average out of them. So for the given network, it was 1.64. which we can clearly analyze that the network we are working with is actually quite uh, well connected. So that's why the average distance is so less. Next cohesion measure is the geodesics distance matrix. It actually returns us n cross n matrix where I comma j is the shortest distance between node I and node j. So in other words, it actually returns us the shortest distance between every pair of nodes. Uh, so that's geodesics distance matrix. Another similar measure is the geodesics matrix. In this matrix, I comma jth element actually represents the number of shortest paths between node I and node j. So suppose we take the example of 1 comma 5. So in the previous one, 1 comma 5, the entry corresponding to 1 comma 5 is 2. So that represents that the number of shortest paths and the length of the shortest paths between 1 and 5 is 2. But in this geodesics matrix, the entry corresponding to 1 comma 5 is 1, which represents that there exists only one path which has the shortest length. So that's it. The earlier one actually, so just to clarify it once again, the geodesics distance matrix is just the shortest distance, and geodesics matrix returns the number of paths between node I and node j having length equal to the shortest distance. Next we'll go on to eccentricity. It just eccentricity of each node is just the largest geodesic distance between that node and every other node. So here the SocNetV actually returns us a report which has the eccentricity of all the vertices. That's it about eccentricity. Next is the diameter. Diameter of the network is the maximum eccentricity among all the vertices. Uh, for the for the known dataset we have taken, this turns out to be 3. Connectedness is the next cohesion measure. It actually just returns whether the network is connected or not. For a directed network, it also specifies whether it is strongly connected or weakly connected. Strongly connect for just to recap, strongly a directed graph is strongly connected if for every pair of vertices I comma j, there exists a path from I to j as well as from j to I. Whereas it is weakly connected if at least one of those paths exist. Like either I to j should exist or j to I. Even both can exist. That's not an issue. So that is the difference between strongly and weakly connected. Walks of a given length. So this actually asks us to enter a length of the walk, and it actually also specifies the range which is available in the given network. So suppose I enter 2, so it actually returns a n cross n matrix where I comma jth element represents the number of walks between node I and node j of the length we had earlier entered. So earlier I had entered 2, right? So I comma j actually represents the number of walks from node I to node j having length 2. So that's walks of a given length, and building upon this is total walks. It also returns n cross n matrix. Here I comma jth element represents the total number of walks from node I to node j. Total walks basically are walks from I comma j of any given length. Walks do not even this note that this is not paths. It is walks. The difference is that in a walk, vertices are allowed to repeat, and so are edges. So since there is no restriction on repetition as well as there is no restriction on the length of the walks, these are the two main reasons why the the entry corresponding to each cell in the matrix is actually quite high. It is an 18 digit number. So it actually returns an n cross n matrix. I have cropped it because as you can see, the if I had included all of the entries, then it would not be even a particular entry would not be visible. So just for clarity, I've cropped it. So total walks is just total number of walks from I to j of any given length. And next is the reachability matrix. It actually reachability matrix just tells us whether the let's take an entry like I comma jth element of this matrix actually represents whether I is reachable from j or not. So the entry is 1 if they are reachable, and it is 0 if they are not reachable, and that's it. That's reachability matrix. Next is the clustering coefficient. Clustering coefficient reflects the degree to which the nodes tend to cluster together. The above formula is actually for directed networks, while the below formula is for undirected networks. The cause of the difference between the two is that in undirected networks, the path, the edge, if there exists an edge between I comma j, then it is actually equivalent. Like I comma j is same as j comma I in undirected networks, whereas there is a difference between them in directed networks. So the two factor actually comes from there. You can also interpret as the two being part of the denominator. That will make the denominator as KIC2, which is the number of possible edges in undirected network, whereas that is not the case in directed networks, since I comma j and j comma I are different in directed networks. So that is the reason of having two different formulas for clustering coefficient. So here is the report which is returned by the SocNetV. Uh, the left side actually represents the clustering coefficient of each of the node, whereas the global or network average clustering coefficient is just the average of all the clustering coefficients which have been mentioned in the report. And another thing which I need to point out here is that in the table there are actually two additional columns as CLC dash and percent CLC dash. So the dash is actually just the normalized version of the clustering coefficient. The dash represents the normalization part, and the percent is actually just multiplying the normalized clustering coefficient by 100. So this is actually consistent with all the reports. Dash is representing normalization and percent is just multiplying the normalized coefficient with 100. So that actually covers all the cohesion measures. Next, I'll be moving on to centrality. This again comes under the analyze section of SocNetV, and as you can see in the below screenshot that there are various centralities and prestige available here. We'll be focusing on mainly the centralities which are part of our network science course. And centrality measures in networks quantify how much central each node is, and how central they are actually also corresponds to how important they are and how influential they may be in different scenarios. And that's why we study different centralities, because each one of them is actually important in various scenarios. So moving on, let's go on to the first one, that is degree centrality. At degree centrality, just for every node, its degree is the number of nodes it is directly connected to or it is adjacent to. So degree centrality is just the degree of a node. We actually normalize it by dividing it by n minus 1, and here you can actually see the difference between DC and DC dash. And DC dash is the normalized version of DC, and percent DC dash is just multiplied DC dash by 100. So that is degree centrality. Degree centrality is often a measure of how active or how directly connected each node is, and it can be computed in both indirected and directed networks. In directed networks, SocNetV by default considers the out degree of the node. The reason for that is that SocNetV is actually a social network visualizer. So it says that in a social network, it gives more importance to how many other nodes a particular node is directly connected to, and that's why in for directed networks by default it actually considers the out degree in degree centrality. Moving on, the next one is closeness centrality. It focuses on how close each node is to other nodes. As you can see in the formula, it is actually 1 upon summation of distances between that node and all other nodes. So the idea behind taking this inverse is that the uh, the smaller the distance between that node and any other node, the closer it is, right? That's why the inverse is taken. And nodes with high closeness are the ones which can actually reach other nodes and many other nodes in few steps. It is normalized by multiplying by n minus 1, where n is the number of uh, nodes in the network. So that is closeness centrality. Next we have is betweenness centrality. If we take a ratio of shortest paths between any two vertices, and with a vertex u lying in the shortest paths divided by the total number of shortest paths between any vertices, and we sum up this ratio for all the shortest paths which exist, then that gives us the betweenness centrality of each node u. Uh, so betweenness centrality is actually interpreted as a measure of control which actor has on the information flow in the network. Actor actually just corresponds to node. SocNetV refers to node as actors because it is a social network visualizer. So yeah, that covers the betweenness centrality. It is important in controlling the information flow in the network. Next is the eccentricity centrality. It is just the eccentricity we saw earlier, but it is the inverse of the eccentricity. Again, the idea of taking the inverse is similar to closeness, that the smaller the eccentricity, the more nodes it is connected to in a few number of steps, so it is closer and it is more central. So eccentricity centrality is just the inverse, and here you can see that there's no need of normalization in this. So EC is actually equal to EC dash in every case. It is already normalized. The last one we have is the eigenvector centrality. So eigenvector centrality for ith node is the ith element of the leading eigenvector of the adjacency matrix of the network. So leading eigenvector is just the eigenvector corresponding to the largest positive eigenvalue. So again, SocNetV returns a report which specifies the eigenvector centrality for each node. That covers the centrality measures of SocNetV, and I'll be handing over the presentation to my friend Aditya to continue on network visualization.
So, network visualization is the graphical representation of relationships among the various elements or entities in a network. So, think of network visualization like a map. It shows connections between the places. In the similar manner, network visualization shows connections between the nodes, and it helps us in understanding complex systems by giving us meaningful insights into the structure, behavior, and properties of the networks. Every visualization technique has its pros and cons, and uh, it helps us identify different patterns, clusters, outliers. Okay, and this information is very crucial for the analysis of various networks. Okay, then network layout techniques. So basically. mm, uh, in SocNetV, there are two kinds of network visualization techniques. One is prominence-based placements and one is force-directed layout. Prominence-based placement. So, placement positions nodes based on their centrality within the network, highlighting the most important and influential nodes. Important thing to notice: these layouts prioritize highlighting the node importance and may not be ideal for analyzing intricate edge structures. These algorithms support all kinds of centralities and prestige measures, and we have a variety of layouts like circular layout, a level layout, nodal size, and node color. Um, Circular layout. So Node in a circular layout, nodes are positioned on concentric circles with the most central node closest to the center. Uh, what are the advantages of it? It clearly highlights the prominence of a certain node. Like in this example, I have arranged them on the basis of their degree centrality. So you can see that the highest degree centrality ones are the ones closest to the center. This is one thing that is only portrayed in circular layout. Like the higher the value of that measure, the closer it is to the center, and they all are in a concentric circles. Okay. On the disadvantages of this is that it is only suitable for very small networks, as when the number of nodes increase, this network can become very cluttered. Okay. And the second disadvantage is a limited exploration of peripheral nodes. On levels layout. So what happens with on levels layout is that nodes are arranged on levels with the more central nodes positioned higher upon the screen. Okay, advantages of this are that it is good for medium-sized networks. Like the circular layout was good for small networks, but this is also good for medium-sized networks. Like this can accommodate around 100 to 200 nodes also without getting very cluttered. Like the circled layout will get very cluttered if we have 100 or 200 nodes, but on levels layout can accommodate up to 100 nodes. These nodes same uh, portray the portray similar kind of traits. Okay, one disadvantage is exactly that we have limited scalability. Like if the nodes increase by a huge number, then we can't do anything. The network will become cluttered in on levels layout as well. And one more a small disadvantage is that uh, the layout may change the edge lengths. Visual representation of connections may not be accurate in on levels layout. Okay, then we have the nodal size layout. So nodal size reflects their centrality or prestige score. This this can be used in conjunction with other layout types for a richer visualization. What happens is higher the centrality score or prestige score, bigger the size of the node will be. Okay, so the advantages is it puts emphasis on the most important nodes, and it can complement with other layouts and give us very meaningful insights. Like alone on its own, nodal size layout is not very informative, but when used with other layouts like on levels or circular layout, like it can be very informative. A disadvantage of this is like it is less informative as compared to the other centrality measures, and its limited ability to show connections. Okay, after this we have force directed placements. SocNetV offers force-directed layout algorithms like Hamada-Kawai algorithm, Spring Embedder algorithm, and Fruchterman-Reingold algorithm. These algorithms simulate physical forces between nodes, resulting in visually appealing layouts that emphasize network structures and relationships. So this approach reveals network structures and relationships as nodes are positioned based on these simulating forces. So first of all, we have the Kamada-Kawai algorithm. This this algorithm models the network as a system where nodes are connected by springs. Each spring has a desired length representing the graph distance between the nodes. The algorithm minimizes the imbalance, aiming for ideal spring lengths. Okay, after that we have the Spring Embedder algorithm. It treats the network as a mechanical system where where what simply happens is the edges are replaced by the springs in this as well. But what happens is if two models are connected with each other, then they repel each other. So in this way we have two kind of forces. The attractive forces uh, because of the spring that has replaced the edge, and the repulsive forces the models provide to each other. One more thing that I would like to point out in this example is that look at the node size. Like we are using Spring Embedder algorithm along with the node size layout from the prominence based layouts. So this way it is more informative. Okay, and then we have the Fruchterman-Reingold algorithm. So it refines the spring embedder model by treating nodes as charged particles or gravitational bodies. So what simply happens is now there is no spring between them. If the two nodes share an edge between them, then they'll attract each other, and if they don't share an edge, then they'll repel each other. So these kind of forces replace the spring forces and the repulsive forces from the previous example, that was spring embedder algorithm. Okay, and one thing is that this SocNetV iteratively changes its positions and lengths to equalize, to balance these forces. Like what happened in Kamada Kawai algorithm was that the algorithm minimizes the imbalance, but in spring embedder algorithm and Fruchterman Reingold algorithm, what happens is the algorithm works iteratively with the positions and the lengths until we reach to an equilibrium position. Okay, after that we have community detection in SocNetV. So community detection is the process of identifying densely connected groups of nodes within a network that are known as communities or clusters. So SocNetV offers various community detection algorithms to analyze the network structures and to uncover these cohesive groups. Uh, by identifying communities, we gain insight into the organization dynamics and functional roles of different groups within the network. This knowledge will be essential for us to understand complex systems across various disciplines. So the first one is click census, finding the tightest groups. Census, SocNetV discovers all maximum clicks within a network. A click is a group of nodes where every node is connected to all other nodes in the group. Maximal clicks are the largest possible clicks within a network. After that, we get a click census report which provides us with a comprehensive overview of these clicks. That click census report includes list of all maximal clicks, like I'm showing one in this example. These are the maximum clicks. So it is a list of all maximum clicks that we have identified. After that, we get analyzes properties of the clicks such as size and frequency. Disaggregation by vertex reveals which node belongs to which click. Like it is very informative, and we get co-membership matrix along with it. Okay, but this much of information is very difficult for a beginner to catch on to. So what we do is we have another census, that is tried census. So a tride consists of three nodes and their connections. Okay, every network has a specific number of trides based on the number of nodes, which is NC3. Okay, so however, when we categorize these trides, we categorize them into only 16 isomeric forms. That, like, if we pick any three nodes from a network, then the tride formed by them will always be in these 16 isomorphic classes. Okay, so how okay, the tride census reveals the count and distribution of each type of tride present within the network.
Now we move on to the hands-on of SocNetV. We will start by installation. For installation, we will simply type SocNetV on the internet and clicking on the first site, we will get this window. Clicking on download, it will simply download SocNetV by following the steps. Opening it will display this window. Now we start by drawing a network over it. So if we choose create random network, there are various options available like scale free, small world, erdos reni, deregular, and so on. If we click on deregular, it will ask the number of nodes which by default are 100. So if we click on 20 and if we make the degree as 3, which because it is deregular, it will be applied for all the nodes. Now we click on OK. It will form a graph of 20 nodes with degree 3 for each. Now we start with the properties of the nodes. If we select it and right click on it, we can click on selected node properties. This will automatically display the node label 7 which is selected. Now node size, we can change the node size from 10 to like 8. We can change the node color to blue. Click on OK. We can change the shape to a triangle, and if we click on OK, we will see the following properties are applied to this particular node. We can also add more nodes from this plus option available on the toolbar. If we click on this plus, it has added nodes here. If we click on minus, it will delete a node. It will ask for the node to be deleted. If we click on OK, it will delete that particular node. The node properties are also accessible from this. It will ask us to enter a node, and if we click on OK, the following node properties dialog box again appears. We can also search for a particular node, find node by selecting that particular node here and clicking on OK. We can also drag nodes by the mouse after enabling this. The particular edges will also be dragged along with them. If we click on this, we can shift the canvas by this hand option. From the options, we can also get some of the node properties like display node numbers, display node labels, and display numbers inside the nodes. If we select this, it will display the node numbers beside this. If we display node numbers inside, it will display the numbers inside the nodes. The following can be enabled or disabled by our choice. In the statistics panel, it displays all the properties of the current network on the canvas, like edges, densities, nodes, in degrees, out degree, weight, etc. In the edit option, there are also the nodes properties which has all the different options like find nodes, add node, remove node, selected node properties, changing the color, size, shape, size, labels, and so on. Basically, all the different options that are available for the nodes are also present in the edit option. We can also select by first clicking on this option, then we can select few nodes, and then on right clicking, we can create a clique out of the selected node, a star, a cycle, or a line. For example, if we create a cycle out of them, then a new cycle subgraph has been created with 5 selected nodes. So we can see it has created a cycle out of these 5 nodes. This sums up the node properties for the current graph.
Now, I'll be discussing the basic functionalities of the network menu. In the network menu, there is an option called New, which creates a new network. Open. Open is used to open a .gml graph from a local computer. Example, if I just click on Open, then I get a .gml format. Like example, if hello.graphml. If I select it and press Open, then I get a preview file of the code of the graph. If I select OK, then you can see the graph formed here, and then you can import the graph in various formats like GML, PageEgg, adjacency matrix, two more sociomatrix, edgeless, UCNet, or graphviz.file, and you can also create from known data sets. Like on selecting that, you get a drop down menu, and there are many data sets, graphs of various data sets. On selecting one of them and pressing OK. The graph is created from that data set. And as already discussed, you can create a random network in the network SocNet menu. And then save as is an option where you can save the current graph. It can be done by just pressing Ctrl S. On pressing Ctrl S, it by default saves the graph in a .gml format. And on choosing save as, like that is Control plus Shift plus S, you can select the format of saving the graph. Export to image, you can export this particular graph to a .jpg format or to a PDF format. And there are other options for exporting, that is adjacency matrix or pagec format. On pressing Ctrl P or selecting the print option in the network menu, you can directly send this particular graph to your printer option. And on pressing Ctrl plus F4, it closes this particular graph. And then SocNet allows various analysis methods like matrix analysis. So on pressing this view adjacency matrix, which can also be done by just pressing F6 on your keyboard, it opens a new HTML web page. Uh, like you get a adjacency matrix where if the for example here there is an edge between 2 and 6, so it represents 1. As there is no edge between 2 and 1, it gives a 0 at that place. So the adjacency matrix is an n cross n matrix where each element is the value of the edge from I to j. And on pressing plot adjacency matrix, you get a plot where if there is an edge, then it will be colored, else it is blank. And again, it also allows to find the inverse of an adjacency matrix directly just by pressing it. You can also get the transpose of the adjacency matrix. We can also find the co-citation matrix, which is basically the A transpose into A, where A is the adjacency matrix. We can also get the degree matrix. There are shortcuts for all these matrices, or you can just go to Analyze, Adjacency Matrix and Matrices. For example, if you want the Laplacian matrix, which is D minus A, where D is the degree matrix and A is the adjacency matrix, you can directly find this. In a Laplacian matrix, the diagonal elements represent the in degree of the node. Now, the next analysis measures, that is cohesion measures, will be explained.
Hello, my name is Animesh Singh and I will continue the hands-on session on cohesion measures and I'll actually show cohesion measures and centrality measures and how we can calculate them for our network. So firstly, I will load a network which we can work with. So I'm going to this create a network from known datasets, and I will select this one. So here we have a network from a known dataset. It has 21 vertices. So let's get started. First, I'll go over the cohesion measures. The first one we saw was symmetry test. So as you can see, the adjacency matrix is not symmetric for this particular network. Next, we can check the distance between two nodes. So let's enter the first one to be 5. As you can see, it actually shows the range of nodes available. So from 5 to maybe 9, I think. Let's see. So they are connected and the distance between them is 2. So that's how you can calculate the shortest distance between two nodes. Next is the average distance. As you can see, this turns out to be 1.6 for this particular graph. Moving on to the next one, we have geodesics distances matrix. This actually gives us the shortest distance between I comma j. So okay, wait, it is actually loading. Yeah. So as you can see here, if I talk about this particular element, uh, this is actually the shortest distance from one. The shortest distance from 1 to 10 is 2. So that is what this matrix represents. Let's go over the next one. Uh, Next we have the geodesics matrix, which represents the number of shortest paths between I comma j. So here this element actually represents that there are 4 paths from 1 to 10 having length equal to shortest distance. So that's geodesics matrix. So as you can see, this is actually very easy to go about this your GUI based whole SocNetV. So the next one is centricity. This actually returns the report in a new tab. So this table actually shows the centricity for each vertex. Next we have the diameter. So the graph diameter for this graph is actually 3. Next, under cohesion measures is connectedness. So this particular network is strongly connected. Yes. If it was, since it is a directed graph, I actually use the word strongly connected, and because it can actually differentiate whether it's strongly connected, weakly connected, or disconnected. So next one is walks of a given length. Let's enter 5 and check. So walks of length 5 actually represents how many walks are there between I comma j having length 5. Here you can enter arbitrary length to see the output. Next we can go over to total walks between node I comma j, and this one it is taking a bit time to, so I'll actually do it again. So total walks, yes. So as you can see, this represents the total walks between I comma j for every pair of vertices, and this number is huge. So this matrix is this way. It's actually n cross n matrix again, as it tells us the total walks between each pair of vertices. So next one is the reachability matrix. The entry corresponding to I comma j is 1 if j is reachable from I, otherwise it's 0. So this is simple enough. Next one we have is the local and global clustering coefficient. represents both. Uh, so it returns the report which has clustering coefficient listed for all vertices and even global. So that's it. That covers the cohesion section. Next we'll go on to centralities. The first one we'll be seeing is degree centrality. It again generates a report which reports the degree centrality for each vertex. Next one we have closeness centrality. Again, it's similar to degree centrality, returns a report which has closest centrality corresponding to all vertices. Similarly, there is between centrality, and eccentricity centrality. And the last one is the eigenvector centrality. So this is how you can actually go over to see and calculate all the cohesion measures and centrality measures. As you can notice that I have skipped a few of them, which is because I've actually covered the ones which are part of a network science course. Other than that, I've actually skipped. So yeah, that's it. Next, I will hand over to my teammate Aditya Sharma to continue on the hands-on session. Thank you.
So, hello everyone. I'll be taking care of the hands-on on the web crawler and the edge properties that of the network. So what we'll basically do in this part is that we'll use YouTube.com. We'll use the tool web crawler, and we'll make a network out of web crawler, and we'll we'll discover the edge properties of that. So for that, first of all, there are two ways to use web crawler. First is in the network menu, we'll go and we have web crawler over here, and the second is the shortcut key shift plus C. So in in over here in the initial URL, we'll copy the youtube.com link, and after that we have two parameters: max URLs to crawl. Max URLs to crawl is nothing but an upper limit to the number of nodes that we want in our network. So for the sake of simplicity, let's have 20 nodes. And max links in each page, what this does is puts an upper limit over the degree of every node. So let's put it as 5, and let's generate a network. So as you can see, a network is being generated using the web crawler. Now this looks very random. So how about we use some visualization, and uh, let's apply some visualization. So here are all the 4 types of prominence based layouts, like radial, on level, node size, and color. So let's apply radial, and for index let's take degree centrality. Apply. So over here you can see that all the nodes that had high degree centrality are closer to the center, and as the degree centrality decreases, they are further from the center. After that, so this is web crawler, and you can take the liberty of uh, exploring with different values of the parameters, but this is what kind of network you'll get. Okay, and let's start with the edge properties. So over here in edge properties, we have display edge option, and this is just used to display the edges if you want to or if you don't want to. Okay, after that, display edge arrows. So, do you want your graph to be directional or but non-directional? That we can do using this. As you can see, as I've removed this tick mark, we cannot see arrows over here. Okay, okay. Then we can change the edge color of it. Let's change it to dark blue. Okay, let's apply this. Okay, now we have changed the color to dark blue. Okay, after that, if we have some negative value edges, so we can put a custom color for that as well. And after that, we have display edge weight numbers. So web crawler by default puts all the weights as one, as there is nothing relevant to put weights on these edges. So that's that. You, this using this you can display you can choose to display or not display the edge weights. That is that. You can change the number color over here, and we can display the edge labels over here. There is no edge label in this network, so that's not something we can demonstrate. And yeah, that's it. Hmm? This covers the network visualization part, and with this we complete our hands-on session and we finish our presentation on SocNetV. Thank you very much.